Hi everyone. In this video we're going to talk about the discrete symmetries of the Dirac equation, which are parity, charge, and time reversal invariance. And then we're going to briefly talk about CPT. So to get started, however, I'd like to talk about something that we all know pretty well, and that's the continuous symmetry of rotational invariance. If we think about how a rotation around some axis n affects a ket alpha, a wave function alpha, then we would say that that's just alpha in some rotated frame. For an infinitesimal rotation, so by some small angle epsilon around the axis n, we can say that the rotation can be represented by 1 minus I epsilon over h bar L dot n, where L is the angular momentum operator, which in this case is the generator of the rotation. So generally for a unitary symmetry operator, S, and I say symmetry in quotation marks because the Hamiltonian doesn't necessarily need to be symmetric under this symmetry operator, but we still call it a symmetry operator even when it's not actually a symmetry for our problem. So we would write S equals 1 minus I epsilon g over h bar is an infinitesimal symmetry operation because epsilon is very small. And g is the Hermitian generator of that symmetry operator. Now, if our Hamiltonian H is actually invariant under that symmetry operation S, then we can write SH, s to the minus 1, is equal to H itself. In that case, we would say we would be able to make a symmetry operation on H psi would be equal to I can put in s to the minus 1s and write it like this. So the wave function would be transformed to symmetry operation times psi, s psi, or symmetry operation acting on psi, s psi, and then the Hamiltonian acting on that would be the same as the symmetry operation acting on h psi in the first place. Furthermore, if I expand s in terms of the generator g, I can write, and we have to remember here that g is Hermitian. And now if I multiply it on the left by 1 plus I epsilon g over h bar, then I'll get or g commutes with h. To order epsilon squared. And because g commutes with h, I would then also say that dg by dt, in the Heisenberg way of thinking about it, dg dt is equal to 0. So that means that if h is invariant under a translation, then momentum g is a constant of the motion, the generated g. If h is invariant under a rotation, then the generator L is a constant of the motion. So now that we've revised our continuous symmetries, it's good to have a look at a discrete symmetry that we're already quite familiar with, which is parity. We define the parity operator P by P on some ket alpha is equal to some mirror reversed alpha, where so this equation sets up the basic requirement for our parity operation. When we apply the parity operator to some state, we get a inverted state, alpha prime, such that coordinates in that of alpha prime are the negative of the coordinates of the original wave function. Because the parity operator here is Hermitian, I can write this as and this shows us how the parity operator changes the positions. In other words, we could say that P, if we multiply on the right by P, we would say that P is equal to minus P. That is, R and P anti-commute. Okay, imagine we have a position eigenket phi, that is an eigenket of position, such that when I use the position operator on phi, I actually get the position x naught times phi itself. Then I might say, well, a good way of writing phi is just by the quantum number that it has, which is phi naught, x naught. So I'll say that my position eigenket is just x naught. Then, if I apply a parity operation to that, I would say x of p of x naught is equal to minus p of x, because these guys anti-commute, as we showed before, equals minus x naught p of x naught. So therefore, I would say that p of x naught is an eigenfunction of the x operator with eigenvalue minus x naught. So I might write that as minus x naught, because that's the eigenvalue. That's the quantum number, is minus x naught. Okay, so that's how the parity operator then would act on the position eigenket x naught. So then what does it do to a wave function? Well, I can take a wave function so the wave function ket is psi, and if I write that in the coordinate representation, then that's psi of x naught, or x naught psi. Then the space inverted state is P acting on psi, such that x naught P psi is equal to minus x naught psi, equals psi of minus x naught. And so the parity operator acts exactly as we expect it to act. It changes x to minus x. Furthermore, we can think about eigenstates of parity, which we might write as alpha. And for these eigenstates, we would have p of alpha is equal to pi of alpha, where pi is some number. But we want, if we apply this p twice, we expect p squared on alpha to just give us back our original wave function alpha. So for that to be true, p squared of alpha equals pi squared on alpha, and therefore the eigenvalues are either +1 or -1. And so all the eigenstates are all the eigenvectors rather are either positive parity with pi equals +1 or negative parity with pi equals -1. For the eigenstate alpha, if we then take this construction that we've made in the past, we'll say that that is equal to plus or minus x naught alpha, depending on pi is positive or negative. But we also know that this is what we wrote before for any wave function, that we can write this, and therefore we would say that the wave function of the eigenstate alpha is either symmetric or antisymmetric, depending on whether pi is +1 or -1. So that's going over a bunch of ground that we probably already know. But now let's think about what happens to the parity operator when we act on the Dirac equation. Now, if we want to have a think about what happens to the Dirac equation, and we want to think about a case which would be parity invariant in the non-relativistic limit, we would think about a central potential. So if it's essentially symmetric potential, we know that we're going to have a Hamiltonian that commutes with the parity operator. So the Dirac equation in the central potential is H equals alpha dot p plus beta m plus v of r, where that r is only the magnitude of r and not the direction. And then under parity, we should have eigenstates which are either positive or negative parity eigenstates, as well as eigenstates of the Hamiltonian. But we see that there is a problem here. If we take r to minus r, and then momentum goes to minus momentum as well, remember momentum is just a derivative of the wave function, then that would change h. In the non-relativistic limit, we would have h proportional to, well, the kinetic energy term would be proportional to p squared, and that would not change sign under the parity transformation. But here the Hamiltonian is linear in the momentum p, and so it will change the sign of the Hamiltonian. And in fact, the kinetic energy term alpha dot p will change sign, but beta m and v of r will not. So we'll have a relative sign difference between the two terms. And so we're definitely going to get different eigenfunctions. So the way to resolve this is that we need to take into account the effect of this parity operator on the spinors. Since we already have that px or I wrote it as R. Since you already have that P, R, P to the minus 1 is equal to minus R, and P momentum, P to the minus 1 equals minus P. So we need an extra unitary operator UP such that our total new curly P version of the parity operator will be UP times the regular parity operator P. And UP will be a 4x4 matrix that acts in spin space. And we want that curly P, H curly P, is equal to H. So in that case, we need UP alpha, UP minus 1, is equal to minus alpha. Why? Because then if we look at this Dirac equation up here, we've got this kinetic energy term alpha dot P. P will change sign under the parity, but if we also have alpha changing sign under the parity, then the total transformations of alpha dot P, the kinetic energy term, will be no change. It will be unaffected. And similarly, we need the other two terms to not change. So we also need, so this is what we actually want from our UP. And if we look at these, can we think of a matrix that satisfies these requirements? It needs to anti-commute with alpha and commute with beta. Well, there's an obvious one. We can take UP equals beta itself. Then beta equals the complex conjugate of beta. And it anti-commutes with alpha as required, and it commutes with itself. So it has all the properties we need. And so in the end, we'll say that our curly P operator, the total parity, is equal to beta times the normal parity operator. And curly P applied to some wave function psi of R is equal to beta times psi of minus R. Okay? So that defines our parity operator for the Dirac equation. Now, a good thing to do is actually apply this thing and make sure that you understand how to do that. In the last lecture, we wrote down some free particle solutions. So I suggest that now you pause the video and apply the parity operator to the wave function that has spin up and positive energy. So if you take this wave function and you apply the curly P operation to it, then you should see what you get in terms of the other free wave functions. And this will give you a feel for what the parity operation does to the Dirac spinners. So next off the block, we've got the charge conjugation. In Klein-Gordon, we saw that for the particle, we would say that that was the wave function for energy greater than 0. While for the antiparticle, it was the complex conjugate with energy less than 0 was the antiparticle. So we look for a similar association for the Dirac equation. And we'll start by taking the Dirac equation with minimal coupling. So remember that in the Klein-Gordon equation, we found that the antiparticles had opposite charge to the particles. And so we're probably going to find the same thing here. So let's start with this Dirac equation and we'll take the complex conjugate of it. So here we see that the complex conjugate changes the first term relative to the second term. So the first term has minus I times gamma mu star, and the second term has just gamma mu star. So if we have a matrix UC with the property shown here, then when we make a conjugation of the Dirac equation, a complex conjugation, and we have the UCs acting on both sides, we will change the sign of the first term, which will make it match the second term. So just checking what that will do to our conjugated equation, we'll have where you can see that we have applied UC on the left and UC to the minus 1 on the right, and then we have applied UC to the left of the wave function as well. So that's exactly the same way that we did it with the parity. So if this thing equals 0, then we're going to be in good stead. So now I use the fact that UC gamma mu star UC is going to be minus gamma mu. That's the property that I actually want. And here I apply it again. I haven't quite determined what UC is going to be yet. So in this case, UC psi star satisfies the Dirac equation with the opposite charge. Okay, so we know what the property that we want for UC is, and now we have to figure out what it is. If we have gamma 2, that one has imaginary components. So it's the one that's going to have gamma 2 star equals minus gamma 2. Right, this is mu equals 2, not gamma squared. Right, so this is just the the y component of gamma. Just write that note in there so you remember it when you're studying. So therefore, if we take UC is equal to I gamma 2, that'll do the trick. So you should check these relationships yourself and make sure that you understand how to get to them. So after all that, the final conjugated wave function with everything is, I guess I'd write it as curly C to match my curly P from the previous, from the parity. And so that one's going to be UC times psi star, which equals I gamma 2 times psi star. And we also sometimes write that one as I gamma 2 gamma naught psi bar, where psi bar is psi transpose times gamma naught, but here I would need to then transpose this guy back again. So we write something like this. So we need to transpose it back to a column vector because otherwise psi bar is a row vector. Okay, so this one's like, that last bit's not super useful for you guys, but it's often written like this, so it's best that you see it. So the conjugation affects the space-time part of the free particle wave function by taking r to minus r and t to minus t. Now would be a good time to go and apply your charge conjugation to the spin-up positive energy wave function, just like we did for parity. So you should go and try that now, pause the video, and see what that looks like in terms of the other free particle wave functions. And what we'll find is that if the wave function represents a Dirac particle with charge plus E in some potential A mu, then the charge conjugated one represents the motion of a Dirac particle with the same mass but negative charge in the same potential. So hopefully you've paused the video and had a little play with charge conjugation to get a feel for it. The next one's a little bit more complicated actually. It's time reversal symmetry. And time reversal is probably better called motion reversal, because we're not going backwards in time or anything like that. All we're doing is changing all of the momenta to the negative of the same momenta. So everything's going backwards. And that's just like playing a film backwards or something like that. And this one's a little bit more complicated because it requires a anti-unitary transformation. And I guess we should have some kind of definition of this. I would say that if we have a transformation from alpha to alpha prime, which is some theta times alpha, or theta acting on alpha, is anti-unitary if the transformed beta alpha is equal to beta alpha star. And remember that star will change the will change the products and the reactants. So everything on the right and on the left will change. Yeah, so that's the time reversal part. And we also require some quantum mechanical property like this one. Where it changes the complex numbers that come before the kets. So for the Dirac equation, we can write our time reversal operator, using the curly T, as some unitary matrix UT, 4x4 matrix, just like the other discrete symmetries had, times this operator K. And K is an operator that forms the complex conjugate of any C numbers to the right of it, of K, but it does not affect kets. So it will affect the wave function in coordinate representation, for example. That would take the complex conjugate. But if we just write it as the ket psi, then it will not affect psi. In general, you can always write an anti-unitary transformation in this form. It will be some other operator times K, and where the other operator is unitary. So this is what it will look like for us for the Dirac equation specifically. So now we want to think about the properties of this curly T that we want. So in order to have this relationship hold, we would want the curly T to change the momenta but not change positions. So we'd also want to change the angular momentum, and so that would make us have to then change the spin as well. So let's just pull up the Dirac equation, and we can just have the Dirac equation for the free particle this time. And so for the left-hand side, let's have a look at the left-hand side first. What we want is that if we then transform with our curly T, and apply it to our conjugated wave function, then we would get something like this. So that's just expanding out the curly t. And k applied to I dt is going to give us minus I dt. And then we'll have kk, which is 1, and ut, the minus 1, which is also 1. And then we'll be left with ut times k applied to the wave function, which is wave function star. I should be careful here and put all my r's and t's in. And that is the same thing as saying I times the derivative of minus t. And this is nothing but our time reverse wave function. So in that case, this part here should satisfy the time reverse Dirac equation. And for that to be the case, we need for the right-hand side that the first term, which is the kinetic energy term, is unchanged, and also the mass term is unchanged. Okay. So to do that, let's now we need to identify the UT matrices. So we'll start with the second of these guys. We will take the second of these equations and multiply it on the left by t to the minus 1 and on the right by t. So we'll get t to the minus 1, t gamma naught t to the minus 1. That's what we had to begin with. We multiply it on the left by t to the minus 1 and on the right by t itself. And then we do the same thing. We multiply it on the left by t to the minus 1 and on the right by t. And then that means that t to the minus 1t is just 1. So then on the left-hand side, we've got gamma naught. And on the right-hand side here, we've got t to the minus 1 gamma naught t, which is k ut minus 1 gamma naught ut k. And now what we can do is we can multiply it by k on the left. So I'll say k gamma naught is equal to, and then I get k times k. So this is times k on left. That means we get, so use, there we go, k. That means we get k times gamma naught is equal to, and k applied twice because it conjugates all the numbers to the right. If you apply it twice, it's the same as just 1. So you get ut minus 1 gamma naught ut k, and now there's nothing to the right of that second k. So that means that we can then say the left-hand side here is gamma naught star because it's got the k acting on it. And then on the right-hand side, we've got ut the minus 1 gamma naught ut. And so that's the first equation that we need. And it's the same as the second equation from the second equation for t, which is this one. Yeah, it's the same as that one. Okay. So next we take the other equation. So we need, oops. So we also need that t to the minus 1 t I gamma naught gamma t to the minus 1 times t. So again, I'm multiplying on the left by t to the minus 1 and on the right by t is equal to t to the minus 1 I gamma naught gamma t. So this is this first equation up here. Okay, I expand that out and I'll get k ut minus 1 ut. There's method to this madness, I promise you. I gamma naught gamma bar k. What I haven't done is put in all of my hats. I'll go back and do that later. Minus 1 ut k equals, and you can see that a lot of these are just going to sort of cancel off. This is k ut minus 1 I gamma naught gamma utk. And now what I want to do is I want to multiply on the left by k again. So multiply on the left by k, just like what we did before. And now I've got kk, so that's 1, ut minus 1 ut, that's 1. K applied to this I gamma naught gamma is I gamma naught gamma star. Then I've got k applied to ut, and then more k, so that thing goes to 1 as well. So everything on the left-hand side just looks like that. Then I've got kk, which is 1. I've got ut I gamma naught gamma ut, and then there's another k on the right, but it's not acting on anything, so I can just leave it off. And now what I'm going to do is I'm going to write this as minus I gamma naught star gamma star. And here I'm going to introduce some additional factor. What I want to do is I want to write this as I ut gamma naught, and here I'm going to introduce ut minus 1 ut, so that's just introducing a factor of 1 between the two gammas. Yeah, and now I can use my equation that I determined before, which is that gamma naught star equals ut minus 1 gamma naught ut. So this part here and this part here actually cancel each other, and I can divide both sides by I as well, and so I get minus gamma star is equal to ut to the minus 1 gamma ut. Okay, and so that's the other requirement that I have. So I need some ut which transforms gamma naught to gamma naught star and gamma to minus gamma star. So the important thing to realize now is that in our standard representation, if we just pick one representation, only gamma 2 is imaginary. So in that case, gamma naught star is actually the same as gamma naught, which is, as we said before, ut to the minus 1 gamma naught ut. And similarly, we would have minus gamma 2 star, which is equal to gamma 2, because gamma 2 star equals minus gamma 2 because it's imaginary. And then that's equal to ut to the minus 1 gamma 2 ut. But we need minus gamma 3. This is kind of a convoluted way of going around it. But minus gamma 3 star, which is real, so that's just minus gamma 3. That's equal to ut minus 1 gamma 3 ut. And same for gamma 1. Therefore, we need to find some ut which commutes with gamma naught and gamma 2, but anti-commutes, but anti-commutes with gamma 1 and gamma 3. And one good option here is gamma 1, gamma 3. And in the standard representation, you can write that as I sigma 2, sigma 2, like that. So put that one in brackets there. In the standard representation. So putting all that together, we would say that T acting on psi of R and T equals R minus T, and it's gamma 1, gamma 3, operator K acting on R and T, or you would say equals gamma 1, gamma 3, psi star, R and T. Okay, so that's the time reversal invariance. And now is a good time to, again, take that free particle eigenstate, the same one that you've used to test parity and charge conjugation on, and try and apply time reversal on it and see what you get. And so that will give you some sense of what t does to a actual wave function. Okay, and the last topic for today is CPT. And so now that we know how to apply charge, parity, and time to a Dirac spinner, we're going to do it. So we'll take C and then curly P and then curly T and act on some wave function of R and T. So we'll do charge first. It's I gamma 2 times the conjugate of the rest of the wave function, which is P, T, psi, conjugate. Okay, and now we'll act with the parity operator. So the parity operator will give us parity gives us gamma naught times change R to minus R. And finally, gamma naught we can pull outside here because gamma naught star is just gamma naught. So I gamma 2 gamma naught. And then for the time reversal, that's gamma 1 gamma 3. And we'll get psi star of minus RT. And that's equal to I gamma 2, gamma naught, gamma 1, gamma 3, and then psi star is equal to psi itself. So the two conjugations cancel. And we're back to this one. And in fact, we can just move gamma 2 over. So a couple of permutations, and we'll get I gamma naught, gamma 1, gamma 2, gamma 3, psi of minus r and t. And this thing has a special name because it comes up a lot, and it's known as gamma 5. And in the standard representation, gamma 5 equals 0, 1, 1, 0, where 0 and the 0 is so remember, this is the 4x4 matrix, which is, a 2x2 matrix of 2x2 matrices. So where I say 1, I mean the identity matrix, and where I say 0, I mean a 2x2 zero matrix. And so the net effect of CPT on a free particle, or on a free electron wave function, is to convert it into a positron wave function. But this is just the beginning, right? So in relativistic quantum field theory, the CPT invariant is actually equivalent to total symmetry between matter and antimatter. And in fact, it turns out that any Lorentz invariant quantum field theory is invariant under CPT. So CPT is a very important concept for building Lorentz invariant field theories. And I think I'll go back and put my little hats on, but that will do for this lesson. So hope you guys have a good time. We'll see you next week.